So let's do one more where we're trying to find a power series solution in this particular form, Cn x to the n, the sum of Cn x to the n of a first order differential equation. So our first step is to get all the pieces we need to make our substitution. So if we were to find the derivative of this guy, since that's what we're going to have to plug into that derivative, or that differential equation, we know we're going to lose that first term when we take the derivative. So that moves that index to 1. And the derivative would be n times c sub n x to the n minus 1. We would bring that exponent down. We would subtract 1 from the exponent. So if we make our substitution, I'm going to have 1 plus x times our y prime plus our y and that's going to be equal to 0. So let's do some distributing here. We're going to have 1 times that sum plus x times that sum plus that third sum so we can actually pull this x on the inside of that one. And the reason we can do that is every term in here will be multiplied by that x. So then if we're multiplying and we have that same base, we would add the exponents. So the new exponent would be n. Now let's rewrite that first sum. Notice that the second two have an x to the n already, so I need this to say x to the n. I need to move this exponent up 1, which means I need to move this back 1. So if we move that back 1 to start at 0, that's going to change these two n plus 1s in here. And then x to the n plus 1 minus 1 would now be an x to the n. So there's where we are. Now notice the second sum starts at 1. The other two start at 0. Before I can combine anything, I need them all to start at the same place. So let's write that first term out here. If we were to plug a 0 in, we're going to get a 1 times c1 x to the 0 plus a sum that now starts at 1 because we pulled that first term out. Second sum already starts at 1. And then if we plug a 0 in here, we're going to pull that first term out. And then we would have all the rest of the sums starting with n as 1. So I'm going to kind of rewrite this. And put those two together since they're outside of the sum. So that's just going to be c1 plus c0. And then if we were to combine all these, thinking about factoring that x to the n out. So we have n plus 1 times c sub n plus 1 plus n c sub n plus a c sub n. And all that's multiplied by x to the n. Let's do a little more combining. So we have n plus 1, c to the n, c sub n plus 1. And if we put these together, we could factor that c sub n out. That will leave us with an n plus 1 there too. And all that's multiplied by x to the n. So remember, we want this guy to be 0. So the only way this can be 0, two things have to happen. First, that has to be equal to 0. And then this coefficient has to be equal to 0. So C1 plus C0 has to equal 0. So that means C1 has to equal negative C0. And this coefficient, n plus 1, c of n plus 1, plus n plus 1, c of n has to equal 0. So if we solve this guy for c sub n plus 1, we would move this piece to the other side. And then we would have to divide by that n plus 1. So you can see the pattern that's going to happen here. Negative c sub n. And that's going to work as long as n equals 1, 2, 3, and so on. And the reason we have to start at 1 here is because the sequence here started at 1. And in fact, we actually see that with that first piece. C1 is equal to negative C0. So let's just list some of these. So here's what we know. Kind of piecing all this together. We know C1 has to equal negative C0. That came from setting this guy equal to 0 and solving for C1. So then when n is 1, we know C2 has to equal negative C1. But C1 was negative C0. So we're going to get just a positive C0 there. If n is 2, going back to this guy, we're going to have C3 would be equal to negative C2. But we know C2 was C0. So we're going to get a negative C0. So you can see the pattern that's coming out with those coefficients there. Let's do one more just for good measure. If we substitute a 3 in, that's going to give us C4 is equal to negative C3. But we said C3 was negative C0. And that's going to give us a positive there. So now that we have this pattern, let's go back to what that original solution was going to look like. So remember what our original solution was assumed to be?
Yeah.
It was y equals the sum from n equals 0 to infinity of cn x to the n. And if we were to expand that out just a few terms, we would have c0 plus c1x plus c2x squared plus c3x cubed, and then so on. So if we make our substitutions in, we know that there was no substitution for c0, right? Everything's written in terms of c0. But we said c1 was a negative c0. We said c2 was a positive c0. We said c3 was a negative c0. And then we said c4 was a positive c0. So all of those have that c0 in common. So if we try to rewrite this as a sum, we could start at 0 and go to infinity. This is an alternating series. That first one is positive, so let's raise the negative 1 to the nth power. And let's write this as x to the n. So there's our series for this differential equation. Now if we compare that to something that we know, just going back to our sheet over here, we have a sum that could be written for 1 over 1 minus x. And that was going from 0 to infinity of x to the n. So if we tweak this just a little bit, we could come up with what that solution would look like. What we have is a negative x. We could actually think about this. Think about it this way. Both of those are to the same power, so we could rewrite that as negative 1 times x raised to the nth. So what happens if we replace x with a negative x? Well, if we do that on both sides of the equation, we would have a 1 over 1 plus x on the left, and this guy would be the power series for that. So this is actually the power series for 1 over 1 plus x. So we could replace that. So there's the simple solution for this. If we wanted the power series representation, that would be our power series representation for that one. So what we're going to see next is how can we expand on this and solve more differential equations.